And yeah, it is my pleasure for the last talk of this afternoon and the last talk of this week to introduce Guillermo Carrión from Universitat Autònoma de Barcelona. The title of his talk is Approaching Higher Limits from Homotopy Theory.
So thank you everyone for staying here Friday at this time. And also thank you for the organizers. I'm going to talk about my thesis project. It's about computing higher limits using model categories. I want to start from the beginning. I don't know if anyone is familiar about higher limits, but I want to introduce a little bit. If you have a small category, C, then and also you have a nice category D, lim and colim defines a functor from the functor category to the output category. And if the category D is nice in some sense, we can derive this functor. I'm going to explain this with more details. One second. Imagine that you have a functor like this, and this is small, and this has all small limits and colimits. So then for every functor, you can construct the lim of f or the colim of f. So then if D has enough projective or enough injective, and as lim and colim functor are exact in some laterality, we can derive this functor. This is the definition of higher limits using homological algebra. For example, if I want to compute the higher limit of f, I take f, and then I have to construct an injective resolution, E1, En, where these objects are injective functors, and this sequence is exact. And then the higher limit of f is just the cohomology of take limit in every functor. And dually, if we want to compute the higher colim, then now we have to construct a projective resolution f p0, f p0, p1, so on, pn, and this colim is just the homology of this chain complex. Then for our purpose, D has to be nice in sense that we have to we need to do here the derived category. So D should have all small limit and colimit, also should be abelian, tensor triangulated. We ask a lot of property to D. So in this talk, D will be abelian group, but also if you want, could be R module for a ring. And but I'm going to do everything with abelian groups. Now we know what higher limits are, but why higher limits are interesting to us? And I'm going to upwards in this list. The command of cohomology of a node can be computed using these higher limits. Also, they appear naturally in abstraction theory. The polyhedral product are a topological space defined as homotopy colimit. So higher limits are involved here too. But my favorite motivation to learn about higher limit in this case, is the Basfield-Kahn spectral sequence. We are topologists, so imagine and take your favorite functor from a small category to topological space. And now we compute the Ho-colim, the homotopic colimit of this functor. The problem is that this, of course, this is a topological space, and maybe this topological space is hard to compute, or maybe we can compute because we don't know how to replace this functor with another that is the nice one to compute the Ho-colim. And when topologists don't know how to do with a topological space, we fight with our tools. For example, we can take the cohomology ring of this topological space, and I'm going to write here. No. And maybe we can compute this because we don't know any property of this topological space, but we can think, okay, maybe we can do this commutativity, and if this works, this is easy to compute. So the short answer is that this is not true, but if we expand this answer, appear the Basfield-Kahn spectral sequence. And there's a way, or there's a spectral sequence in the using the higher limits of the cohomology group that cover the cohomology of the Ho-colim. This is a first quadrant spectral sequence, and if we know that every higher limit vanishes, then we have the commutativity that we want. If lim I are 0 for every I, then this hold. This property is important, and we say that given a functor f from C to abelian groups is lemma cyclic if every higher limits are 0, and we say that is colemma cyclic if every higher limit higher colimit are 0. Then we want to higher limits become 0, and there's well-known condition that implies colimit acyclicity and colim acyclicity. Clearly, if F is injective, then F is his Owen injective resolution. So trivially is lemma cyclic. And also if F is projective, for the same reason is colimma cyclic, sorry. Also, another condition is if C is the poset of natural number, then F is a tower of abelian groups, and we have here the Mittag-Leffler condition. Also, Diaz introduced the concept of being pseudo-projective. That is another condition to be colimma cyclic. A functor is said to be pseudo-projective if If you have here the poset, for example, like this, you take an element P and take a subposet whose elements are less than P. And then for every j in J, you take an element xj and sum everyone in P through the functor like this. Then if if F is pseudo-projective, this condition implies that every maximal object is in the image of the functor. That means that X, I think this is better, Xj is in the image. It means that Xj is F I J ij for any I. So this condition is hard to check for every, because for every P you have to take every subset, and then you have to take every collection of elements that that makes this sum 0. And we prove that this condition is equivalent to the following. If for every P in P, this natural map is a monomorphism, then the functor is pseudo-projective. Observe that this is an abelian group, also is an abelian group, and we only have to check that a map between two abelian groups is a monomorphism. That is more easy than check the another condition. If any of you are familiar with model category, this condition looks like to be cofibrant in some sense, and we use the machinery of model category to prove things. From now on, every poset is like this, equipped with an order preserving map or an order reversing map. And for short, we say that a poset with an order preserving map is said to be P is a ready poset. Because in this way, if P is equipped with an order preserving map or reversing map, P is a ready category. And using the Kant theorem to this ready category and the model category of cochain complex with the injective model category, we have this model category where weak equivalents are pointwise weak equivalents and fibration are pointwise fibration. In this model category, every pseudo-projective functor is cofibrant. This is just the definition of to be cofibrant and is equivalent, because if P is a ready poset, then P has the DCC condition. If we dualize, we have the projective model category. Now we are working with cochain complex, but are unbounded, so it's quite similar. Again, weak equivalents are pointwise weak equivalents, and fibration, and cofibration are pointwise cofibration. And now an object is fibrant if the natural map, this one, is an epimorphism. We have the following proposition. If F is cofibrant by the previous theorem, we know that F is pseudo-projective, and by Diaz, we know that is lemma-cyclic, co-lemma-cyclic, sorry. But we can prove this directly, and also the dual proposition, because if F is fibrant in the projective model category, F is lemma-cyclic. And to prove this, this proposition is a corollary of the following. Of course, now we are going to focus in the projective model category, but everything I'm going to tell now is easily dualized. So everything is also true if you make if you are working with the injective model category, but you have to make a little change, but it's not hard to convert. And this proposition is that has the previous one as a corollary. If we have a redeposit and a functor, and we have a functor, then we can compute higher limits using fibrant replacement instead of our injective resolution. That means that now we can compute higher limits using only model category tools, and we can forget to take an injective resolution. This new way to compute this give us new vanish result and also give bounds on where these limits vanish. Just for recall that an object is fibrant if the natural map, this one, is an epimorphism. I think I try to not use a lot of notation, but sometimes maybe I say matching, I think it's 2T, to this limb, because it's the notation used in like this in the ready categories. And the problem to construct a fibrant replacement is just to fill this diagram. So in every step, we are looking for a cochain complex here that make a factorization of this map through a weak equivalence followed by surjection. I'm going to explain this with more details, but recall that if P is ready, there is a order now reversing map like this, and this is like a filtration. So here is the filtration, and imagine that in this part we have our diagram. Then there's object in degree 0, also in degree 1, and in degree n. And we can imagine that the matching object is in these bars because it's like an intermediate object. So if here we have a P, then the matching object of this P is 0 because the index category is empty. So this map trivially is a surjection. And imagine that we have here another point and the matching is also surjective. So then if is surjective, this is also a equality. And if everything is okay, we repeat the process, putting in here the original functor. So imagine you are walking through your diagram over there, and then you arrive at a point here, Q, and this map is not a surjection. So here we have the first problem. We have to solve this diagram, and now we are going to use homological algebra tools. As I assume that everyone knows about the mapping cylinder. Mapping cylinder give you a factorization like this. And it's not the factorization that we want, but there is a dual concept that is the mapping cocylinder that I'm going to introduce you now. And we don't care about what is his degree part, or neither what is the differential, because we care about this factorization. Later in an example, we compute this explicitly and make this easier to understand. But the factorization is the key here and is given by this by this formula. C is sent to be to C0 FC, and a point C D prime is sent to be to D. Is easy to see that this map is surjective, and there's no problem in to see that this map is quick equivalence. If you are not familiar, I highly recommend Weber's book. Is an introduction to homological algebra. I can't remember the chapter. I think it's in 1 or 2 is earlier, and he speak about mapping cell agenda, but is similar. And okay, this is a way to solve the problem, but the solution is not good enough. I want to say two things now. First, remember that this lim is computed like this, and as the limit on chain complex is computed degree-wise, if we can make this short in some sense, is a chain complex. So if there's a point where everything is 0, we have immediately a bound of when this is 0. So first we have this, and also I want to remember with you this theorem. If you have a poset P and you have a functor here, we know that these higher limits vanish if I is greater than the length of P. That is the length of the maximum of the length of the chains. So what's happened with this result with the construction that we are doing here? Imagine here again, this is the filtration. And here is the height. So here is filtration 0, 1, here M. Now again, we are walking through our diagram, and when we arrive at M, we have to put here a cocylinder. Then we have to put here the vertical line, because now we are in height 1. What happened? If you remember the diagram, this map is a map between a cochain complex concentrated in degree 1, and now here we have degree 0 and degree 1. So it's impossible to put here again the identity, so put the imagine of the functor, the original functor, because it's impossible that this map could be surjective. So again, we should put here another cocylinder, and this bound becomes linear um, with this. So we improve the bound, but not well enough. So we are going to now focus in the problem again, and observe that this is concentrated in degree 0 and this is bounded, because if you are putting a cocylinder every step, here there is a finite steps. So this limit is bounded, and it's something like this. So now look in your table and take your favorite scissors and cut the functor, the diagram by the dashed line here. I'm not good drawing, sorry. And now we call this D, and we can put here in the factorization the cocylinder of the map FP D. What is this? I put here, this is FP times the matching on 0. Here is lim 0 times lim 1. Okay. Here is lim n minus 2 times lim n minus 1, and here lim n minus 1. So here, this map is by definition of, by the proposition previously proposition, this is weak equivalence, and this is surjective, this is surjective, and this is surjective. So what can we put here? The solution, if D is surjective, we put here D. And then every single arrow is surjective, and also we have to check that this commutes. This is also easy to see because this is the projection on lim n minus 1, and also this is, if I name this D0, this is P lim n minus 1 minus D0, and this composition is the same that this composition, because this composition is 0. So let's put a name of this. If we have a map with this shape, that the first one is concentrated in degree 0 and the second one is bounded, and also the second one has his last differential, non-zero differential map surjective, because this is 0. We call this map truncatable, and if the map is truncatable, the truncated mapping cocylinder is give us the factorization that we want. I don't say it before, but at this, if this is epsilon sub p, this is the mapping cocylinder, truncated mapping cocylinder of epsilon p. So how we construct this fibrant replacement? So easy. We walk through our diagram and checking that every map to the matching object are surjective. If they are surjective, we put the original functor. When we check that one is not surjective, we see, is truncatable? Yes, then mapping truncated mapping cocylinder. If it's not, then the usual or traditional mapping cocylinder. And the maps is given by composition of the maps introduced in the previous proposition. So we reduce our problem into C when we can truncate. Here is our diagram, and we have to check two things. The first one is if P is reading, then for every P, this category is also a ready category. And given a functor, this functor restricted to this category has this functor is also quick equivalent to this one, because the weak equivalents are pointwise weak equivalents, and also this is Fibrant 2. So this one is his Fibrant replacement. Then by proposition, the proposition of, I think it was the first or second proposition, this is the way to compute the higher limit. And if we look at the height of the matching object, I mean, here is I is n, then by definition, this is the kerr of 0, imagine of D, but this is lim, n, which is this. And if we know for any reasons that this is 0, then this implies that D is surjective. And then this implies that this map is truncatable. So we can resume this in the following theorem, that is the main theorem of this talk, that if you have a redeposit and you have a functor from this redeposit to abelian groups, if you can find a bound of higher limits in these subcategories, then you have a global bound, but you lose the equality. I know that this maybe is hard to understand what this theorem says, and I want to do two toy examples to understand what is happening. But yesterday I was talking with Wilson, Alex, and Thomas, and they asked me if I have a example of why we lose this this equality, and I want to told you now. The example is the example 2. If you have here, for example, G0, G1, and G2, and we put here 0 and 0, and we want to compute, sorry, we don't need that this. We put here two maps, F1 and F2, and we want to replace this functor. We put here G0, and now we have to know what to put. Oh, sorry. Here. Of course, this is G0 and these two. So if these maps aren't surjective, we have to make the replacement, and there's no much space to truncate, so this should be the mapping cylinder. So here we put, oh, sorry, G0 times G1, and here G0, and similar here, G2 times G0, G0, and 0, 0. So here is the projection on G0, here too, oh, sorry, G0, and here the map is the identity minus F, oops, F2, and here is the identity on G0, sorry, G0 minus F1. So if we want to compute this higher limit, we should compute the limit of this. Of course, is degree-wise. So this is G1 times, in order better, G0 times G1 times G2, G0 times G0. And the differential is G0, G1, G2 is G0 minus F1, G1, G0, F2, G2. So if one F1 or F2 is surjective, lim1 is 0, but if the two maps are not surjective, then there's something in lim1, and this is an easy comproval of linear algebra. And now if we want to know something, what the theorem says, sorry, I'm really uncertain here. But the theorem tells us that if we apply this theorem as the lim1 was G0, there's nothing here, so now n is 1, but now knows that here are lim1. And I want to now explain two examples more. The first one is this well-known result. If you have a simplicial complex of dimension m, then there's no cohomology groups if I is greater than m. And we want to prove this using the previous result. First, we need a theorem, okay, a corollary is the corollary 5,4 on the Ansbach-Kessar-Oliver in the fusion system in algebra and topology. That if you have a C and small category and you have the constant functor from C up to a B, then this limit is the cohomology of the nerve with coefficient mg. So with this, we can prove, with this and also the previous theorem, we can prove this result. So first, if you have a simplicial complex and P is the phase poset, then this is a reading poset. And the filtration is given by the dimension of every simplex. And observe that if you have a simplex, then this category is just the phase poset of the boundary of the simplex. So observe that trivially this has the homotopy type of an sphere. So we know these groups, and we want to compute this for the constant factor by this result. This is with coefficient on G, and we know that this is 0 if I is greater than this n, but also if we don't want to be more precise, we can put here the dimension of the simplicial complex. So we have that for every sigma, this higher limit are 0 if I is greater than the m. So by the theorem, we know that this limit are 0 if I is greater than m. Here we lose again the equality, and also is a counterexample of that we can have the equality too. And also this is by echo the cohomology of K. I don't know if this theorem, if this example is clarified, but I want to tell you that this theorem speak quite like dimension of the poset in some sense of the functor. And this is an example that if the things goes bad, like in simplicial complex, that every time is growing the dimension, then we can do anything, because you cannot truncate if every time you are growing the dimension. And to finish my talk, I want to talk about abelian groups, towers of abelian groups. That is another example that we cannot improve this bound. Of course, a tower of abelian group is a functor from the poset of natural number up to abelian groups, and is usually represented like this. Of course, if n is a natural number, then this category is just 0, 1, n, and this has a final object. Then this limit are 0 if I is greater than or equal than 1. Applying our theorem, we know that this limit of g are 0 if I is greater than 1 or equivalently are equal or are greater or equal to 2. And to prove this, we only said that this has a final object. So we can extract as a corollary that if P is a redeposit such that for every P, this subcategory has a final object, then this limit are 0 if I is greater or equal to 2. But of course, a category poset with this property P is a 3. And there's another possibility to P. And that's all. Thank you very much.
Thank you, Guillermo. So let's now start questions or comments. Or remarks. Jérôme?
Maybe I can ask a question.
Of course.
After these toy examples, what are the next ones you want to solve? Are they related to fusion systems, to poset of subgroup, things like this?
Now we are looking for a combinatorial bound. We have almost a combinatorial bound, only using the shape of the poset. And maybe when we take this bound, we sweep to fusion system maybe, or category of orbits. I don't know exactly where is the way.
Okay, thanks for the answer on the talk. Thanks.
Thank you.
I don't know if there can be any relation between this method and trying to compute higher limits by filtering the functors, which is used sometimes in work related to fusion systems.
Sorry?
I don't know if these methods that you are using can be compared with or have any relation with the filtration of functors by atomic factors. No?
I don't know, because we use hardly the condition that P is a ready category. Atomic functors. I don't know. I'm sorry.
Can I make a comment?
Yes, please, because I don't get.
I think, Carlos means that the standard technique is to reduce to atomic functors. You remember that you look at
a filtration of the functor with quotients are atomic.
Atomic functors. Yeah.
Yes, we are trying to compute also these two atomic functors, and we make a short computation with small functors, but the computation is not easy because sometimes there's no way to truncate this functor because everything is 0 everywhere.
There is a question in the chat.
There's some...
You can make your question yourself if you want. How?
I can read it. Why? So, are there some results on the multiplicative structure on the biological kind of spectral sequence?
I don't exactly know because I'm only use this to. So I only know about this Basfield can spectral sequence like a layman, only to make some examples.
I wanted to ask a similar question. So what cohomology are you using just ordinary cohomology, or what you have done is also good for other cohomology theories?
For any
Yes,
cohomology.
Imma, you can ask.
No, well, I think that as long as the systems fulfill the conditions, it's applicable to a lot of theories.
Yeah.
And it generalizes like the Mittag-Leffler kind of conditions that we are familiar with in a very, very wide number of cases.
Yes.
I mean, you just need to sit and check. I mean, of course, the restrictions of the redeposit, etc. I mean, this is strong restrictions, but I think that many things that have been done like by hand, case by case, and many of these computations I was trying to do like by hand in my master's thesis or in my thesis, like computing limits in a particular theory can possibly be simplified, just checking if you are lucky enough that you fulfill some of these conditions.
Okay, there might be some other question. Yeah, if not, then Guillermo, that was a very nice talk. Thank you, and keep going on. Thank you.
Thank you.
For the courage of being the Benjamin of the conference. That's not easy.